And I have another one of these assignments where you go into the real world and get some real world data. I verified today that that data is available, and it's not the sort of thing where you have to put in a request and they email you later. It's just there, ready for you to get. But all the same, maybe get the data sooner rather than later, so that if maybe this government website crashes or something, that, or let me know if you have trouble, because I do have a local copy of the data file that you need for that evaporation assignment. It's due next week. And I was looking over the schedule. Also next week we're going to have our second quiz of the semester. It'll only be covering 2 lectures. It'll be covering tonight's lecture and the previous one. So since we've started talking about the hydrologic cycle is what's going to be included in that. So any questions related to the announcements? Well, we're going to begin by looking at a couple of videos to set the stage, to prepare our minds for evaporation. Let's first watch a time-lapse video. You can say that tonight in class you watched water evaporate. I mean, how's that for a productive use of your time? They say watching paint dry, but this is even less exciting because at least paint is a color. This is a clear substance. So we're going to watch water dry. This is a time-lapse picture. It's over even before it began. Let's watch it again. I think the computer locked up. Playing YouTube is simply beyond its abilities. Oh, it's so pathetic, man. Oh, wait. I want that one I just watched. All right. So it's evaporating, and so I guess there are a couple of things that we can notice about the way that it's evaporating. Why do you think it evaporated on the left side of the screen before the right side? Like, what's special about where the water still is? Like, why didn't it evaporate here compared to there? Less water, so it's a low point. So maybe if it's evaporating at an even rate all over, different parts of the concrete are lower than others. I think you're right about that. Now it looks like this entire area is in the shade. It looks like here is the line of shade. And this is maybe under a carport or something. Here more is exposed to the sun. And of course, I think we all could agree that any water that was on this part of the concrete that's warmed by the sun would evaporate a lot more quickly. So it's just sort of instinctive that there's a relationship between heat and evaporation. We all kind of know that. Let's watch what is called the Leidenfrost effect. And it's when evaporation can occur so quickly that it creates a cushion of air. So they poured water into a hot skillet, and it's just sort of dancing around on that skillet. And so now here's another illustration of the speed of evaporation being affected by some energy source. So that time lapse was slow. I don't know over what period that first video was taken, since it's a time lapse. It maybe is an hour or 2 hours. But this is just a couple of seconds that this water evaporates. And so the speed of the evaporation is affected by the energy available to do the work of evaporation. And actually, evaporation is work. It's a change of phase from a liquid phase to a gas phase. And there's a certain amount of energy required per unit of water to do that work. And so here, the work is being done very quickly because of the burning gas underneath the plate. All right. Now, of course, water evaporates differently in Canada than it does in the United States, because of socialized medicine and whatnot. So let's see how water evaporates in Canada.
What are you doing, Sam?
These guys are up in, I think this video is from Yellowknife. Oh, it says up here, Yellowknife, yeah. So that's really far north. So you've done that? I tried doing it here back when we had below zero, I think 2 or 3 years ago. It didn't turn out that good. It was pretty interesting, you know, but this is better than I was able to do it. So why do you think it's going into a vapor so quickly? Anyone want to offer their suspicion on what's causing it to go straight from a liquid into a vapor? It's almost, it looks explosive in a way. Why is it doing that? And why does it have to be from the tea kettle? She was using a tea kettle. Why? Pressure. I don't know if it's pressure. I mean, she was just pouring it. It's boiling. But why? Yeah. But why? Why is it boiling water? Why didn't she just get ordinary water from the faucet instead of heated water? Why do you think it's got to be heated water? Huh? It'd freeze? That's possible, yeah. Have you heard of, I mean, you know the idea of gradients or a driving force. You know, the further apart two things are, the faster the reaction is. You know, in chemistry, you learned a lot about if you remove the product, then it speeds up the reaction. If you have a lot of reactants, then the reaction will be fast, but then over time, a chemical reaction slows down as more product is in the same location. And so you have to keep removing the product of a reaction because the driving force is affected by the buildup of a product. And so here, I think one of the principles that's illustrated is that when there's a really big difference between the water temperature and the air temperature, then that speeds up the rate of evaporation. And so that's one of the things that we'll get into the details of today is differences between air and water temperature and why that affects evaporation. So, I mean, she could have thrown tap water in the air and maybe some of it would have vaporized, but probably more of it would have just, the droplets would have hit the ground as liquid or maybe as ice rather than going to the vapor phase immediately, you know, straight into a gas. Excuse me. All right, one more video. And this is interesting because it's showing evaporation in a situation where heat isn't being added. Now this is a specialized case that actually doesn't play a role in what we're talking about today. But here someone has a mason jar and they're connecting it to a vacuum with that tube, and the top is sealed, and so they're sucking out the air, and by sucking out the air that's above the water, they're removing the pressure that's pushing down on the molecules and keeping them trapped in the liquid phase. Because, you know, what causes evaporation is collisions of molecules. As soon as a molecule of energy has, a molecule of water has enough energy, then it can escape into the atmosphere. And so the atmospheric pressure is pushing down, trying to resist that escaping pressure. It's called the vapor pressure. And so when you're boiling, you have equilibrium between the vapor pressure of the water and the atmospheric pressure above the water. And so here, by removing the atmosphere and the headspace above the water, what they're doing is they're not adding heat, but the boiling, or which is a transition from the liquid phase to the vapor phase, is simply accomplished at a lower temperature than it ordinarily would. But this is mainly a curiosity for our purposes today. We're going to be talking more about evaporation due to heat addition. Any comments before we continue? Still mystified as to why this monitor went off. All right. Oh, there it's back. The energy that causes evaporation comes from the sun. And the solar radiation that comes in and hits the Earth's atmosphere is at a different wavelength from the radiation that goes out after it's either reflected or emitted from the surfaces that absorb radiation. And so this is showing two distinct spectrums. The incoming solar radiation is a short wavelength, and the outgoing radiation that's emitted from the Earth's surface is a long wave radiation. And this kind of gives an idea of how much energy there is. This is a similar diagram to when we were looking at the amounts of water, the water balance, where we had evaporation from the ocean was the source and sink of all of the water. Well, the source and sink of all of the energy, if we do an energy balance on the Earth, is space. And so it's broken up into three basic rows here. One row is space, the atmosphere, and then ocean and land, so the surface of the Earth. And what you'll notice is that there's something called the solar constant, and that's how much energy is actually coming from the sun and makes it to Earth. And so if you're up above the atmosphere, which filters out some of that radiation, you know, when they build a satellite and they put the photovoltaic cells to try and power the satellite, the maximum amount of energy that they can get from those cells, if they were 100% efficient, would be 1,367 watts per square meter. Now, they're far from 100% efficient. I think maybe the best they've ever done on a PV cell is below 20% efficiency. But that's how much radiation is coming from the sun by the time it gets to the Earth. So we're considering that as 100% of the solar radiation. Now, some of it is just what's called backscattered by the air, where it doesn't even come close to the clouds. It's just reflected by the molecules of the air themselves, and it's reflected back into space, still as shortwave radiation. The long-wave radiation only occurs when the incoming solar radiation has been converted into heat, and then that sensible heat is emitted at a longer wavelength. And so this solar radiation at the short wavelength isn't necessarily heat, but it can be exchanged into heat. So a small portion of the radiation is reflected by the clouds. That's the 20% that you see, the reflection. Some is reflected by the surface. Some is absorbed by the clouds. But only about half of the incoming solar radiation is actually absorbed either by the land or by the ocean. Now, if any of you have ever seen that documentary, An Inconvenient Truth, how many people have seen that? It's the one with Al Gore about global warming. Well, one of the, I think, the best technical points that that documentary makes is that ice is far more prone to reflect solar radiation than water is because of the difference in color primarily. You know, at the North Pole, when it's snow and ice, that's white, and lighter colors are much more able to reflect solar radiation. And so the point that that movie makes is that when ice melts and turns into water, then the water is very good at absorbing the radiation. And so it becomes kind of like a positive feedback loop where if you get a puddle of water at Greenland, for example, then that water is absorbing, whereas previously if it had been just snow or ice, it would be reflecting incoming solar radiation. And so then that warmed water melts more water, and so the puddle grows larger and larger and larger. And so one of the things that's changing over time as the climate varies is the fraction of the solar radiation that is either reflected versus absorbed. All right, so 50%, roughly speaking, of this 100 units of incoming solar radiation is absorbed, and then it has to be emitted. If it was kept within the Earth's atmosphere, then the Earth would slowly, well, not slowly, it would be heating up very quickly. You know, global warming or climate change is a process over decades and decades, the Earth's atmosphere increasing by maybe 1.5 degrees Celsius, maybe 2 degrees Celsius. But it would heat up a lot more quickly if there wasn't an emission of the absorbed radiation. Now that long wave radiation, it goes out as emission from the surface. Net sensible heat flux is, that's the sort of, those are thermals. You can think of it as like the heat waves that you can kind of see going as you're driving over a long road on a hot summer day. You can see kind of like the shimmering of the surface. And that same fraction of radiation that came in eventually goes out. Now there are some patterns to the incoming solar radiation being low wavelength, outgoing radiation being long wavelength. And there are variations based on the shape of the Earth's surface. And this is a nice diagram because it shows if you have radiation coming from the sun, and this is representing maybe, think of it as a square meter. And so the shadow that that square meter casts on a curved surface like the globe, at the northern and southern latitudes, those shadows are very large, which means that the solar radiation is spread out over a wide area compared to the equator. And so the angle of incidence has an effect on how intense the sun is. And so at the equator, you burn very quickly because the incoming solar radiation isn't being spread out over a curved surface in the same way. And so if you've ever been like in the mountains, you know that you can get a sunburn really quickly in the mountains. Now that's partly because there's less atmosphere at higher elevations, and so more sun is getting through and not being reflected by the atmosphere. But near the poles, it's simply that even at ground level, there's more radiation than there would be here in North America. Another kind of interesting way that the solar radiation that's responsible for evaporation varies over time is just the fact that during the course of the year, the Earth is different distances from the sun. Not by a lot, but by about 1 or 2%. You can see that during the autumn and winter months, it's 146 million miles, and during the summer months, it's 151 million miles. And so the closer we are to the sun, the more intense the sun is. And then also you can see, and you already know, that the Earth tips back and forth through the seasons. And so that exposes more of the radiation to the northern latitudes versus the southern latitudes and vice versa. So we don't need to dwell on that. But like some of the videos illustrated, evaporation is due to energy being available to volatilize water. And there's a really fascinating write-up from a weatherman in Cincinnati, Steve Horstmeyer. I'm not sure what channel he works for. He may even be retired at this point. But he put together a page just to kind of debunk some of the common thinking about relative humidity, because a lot of people don't understand the relative in relative humidity. The relative means that it's a percentage of how much moisture can be in the air for that temperature. And we previously have talked about the adiabatic lapse rate when we were discussing how the temperature changes as you go up through the atmosphere, just as a function of elevation. And the idea there is we were in discussing clouds and why it rains. And the main idea behind why it rains is that as warm air rises, it's cooling off, and then it's less able to hold on to the moisture in it, and so it becomes fully saturated. And so that was when the relative humidity kept increasing and increasing, because, not because there was more liquid, but because the temperature was decreasing and the capacity of the air to hold on to water goes down as the temperature decreases. So this goes into a really detailed explanation about relative humidity, and it makes the point that most people think that they've felt 90% humidity on a 90 Fahrenheit day, but that in Cincinnati, no one has ever felt that. Like he looked at the historical data, and there's never been a 90-degree day where the humidity was 90%. He says that there's only a couple of places on Earth that it's been both that hot and that humid, because the air has so much of a capacity to absorb water at higher temperatures that it's very difficult to get that much water into the air when the temperature's that high, because the solubility of water is very high at those temperatures. So there are a couple of main points, concepts that you need to remember, and that is not all molecules have the same kinetic energy at a certain temperature. And so think about a basin of water, and in that basin there are billions of water molecules, and they're moving around and they're bouncing into each other. And so some of those water molecules are moving slowly and some are moving quickly. Just think about a normal distribution. Everybody's familiar with the idea of the bell curve, right? And so most of the water molecules are going at some average speed, but there's a small fraction that maybe a molecule got bumped into 3 times in a row in the same direction, and so now it has a lot of energy. And there's not very many of them that had those successive collisions in the same direction. But a small fraction of those will have a lot of kinetic energy just because of whatever random collision patterns that have been occurring. And that small fraction of high energy molecules are the ones that evaporate. And so over time, the rate of evaporation is just affected by how quickly the water molecules are moving around. And of course, they move faster as the temperature increases, and a greater number of them will have that high energy state at a higher temperature. So when I say that there's a distribution of kinetic energies, that's just recognizing that although we can put a thermometer in a basin of water and measure the temperature of the water, that doesn't mean that every molecule in there has the same amount of kinetic energy because they're colliding. Kinetic energy and potential energy are different things. And the potential energy may be related to the temperature of the liquid, but the kinetic energy is related to the movement of the liquid molecules. That's an important point. Any questions about that? Anybody feel uncertain about the main idea? So once the water evaporates from being a liquid and it gets up into the air, it can only stay in the air as long as there's energy in the air to keep it suspended. You can think of it as either dissolved or suspended because the water is dissolved into the air. And so at night, as the air cools, the relative humidity increases until the water precipitates out. And you've probably heard the phrase the dew point before. And the dew point is where it's not necessarily raining, but it's a temperature at which for how much air is in the water, I'm sorry, how much water is in the air, it's when that water will start to like coat the surfaces. And so your car gets wet. If you're sleeping in a sleeping bag or a tent, all those surfaces will become wet late in the night, early in the morning because of the cooling that occurs overnight. Okay, so here is a diagram that's showing the water layer, and some of those water molecules are escaping into the vapor phase. And so we have oxygen, hydrogen, so H2O. In the atmosphere is nitrogen, mostly, 80% nitrogen. And so part of what's preventing all of these molecules from just escaping into the atmosphere is that the nitrogen pressure pushing down means that there have to be enough kinetic energy to escape and to get into that vapor. Do you know how we measure the amount of gas molecules above a liquid layer? Like, atmospheric pressure talks about all of the different things that are in the atmosphere, like the nitrogen, oxygen, there's some helium, carbon dioxide. But each of the gases can be measured as a partial pressure. And do you remember talking about partial pressures in chemistry? Since oxygen is about 20% of the atmosphere, then the partial pressure of oxygen is 0.2 atmospheres. Or you can multiply 0.2 by whatever pressure measurement you're using, whether it's 760 millimeters of mercury or whatever. And so the amount of gas above the liquid we measure in partial pressure. Another thing to point out is because the molecules are so spread out in the atmosphere compared to the liquid layer, they can't heat up the water very quickly. It's not the air temperature warming up water. It's direct sunshine that warms up water quickly and can really drive evaporation, because there's simply not enough mass in air to have a really big effect on the water itself. The water has a much greater density. Now, the amount of water molecules in the liquid isn't measured as a partial pressure. We can measure it on a mass basis or on a molar basis, but there's the difference in phase comes with a different way of measuring the quantities. Now, another thing that, just a concept you need to really internalize and be able to explain is what causes liquid water molecules to vaporize. That idea of kinetic energy and molecule collisions leading to enough kinetic energy to escape from the liquid phase. We've talked about that already. So globally, the average amount of evaporation is 3 millimeters per day. And that's talking about, at the equator where the solar radiation is very, very high. And so it's driving a lot of evaporation. And that's also including the northern and southern parts of the atmosphere where the evaporation is low. And so it's kind of a global average. So here's how much water, how much energy it requires to vaporize, how many joules per kilogram of water. So 2.5 times 10 to the 6th minus the temperature. And so the amount of energy required to vaporize it varies by a function of the temperature of the water itself. And so warm water requires less energy to vaporize than cold water. And we're going to use this formula later on when we're calculating and estimating the rate of evaporation. All right. This is a picture that I took while I was driving on Route 2 a couple of years ago. I shouldn't have been taking pictures while I was driving. I admit that. But the science was just too interesting. Let me dim the lights a little bit so you can see that picture. All right. What do you notice about the clouds in that picture? Directly over the river. And it was a perfectly clear day. It was only over the river. There wasn't a cloud in the sky except for 300 feet above the river. So why do you suppose that is? Well, this is in the morning. I was driving towards Huntington, so I know it's the morning. Why do you think that there were clouds only over the river? Well, one thing that that's unique about the river is that it's warmer over the river because the water holds on to its heat longer than the land does. At night, the water holds on to its heat a lot more than the air does. At night, the air will cool, but the water remains warm. And so here we had a cool atmosphere and then a warm river. And so the river is both a source of heat and a source of moisture. And so there was evaporation occurring from the river, and the water that's in the air is rising, and then it got to a certain point where it was cooling because it was rising, and so that cloud is those are the same water molecules that had just evaporated now beginning to condense. And so it's kind of like the hydrologic cycle right there in front of you, just one picture, the evaporation and the subsequent condensation. Now, it wasn't raining. There wasn't like a sufficient nucleation of all that condensation. I think what probably was happening is that the clouds were then just sort of diffusing in the same way that smoke would But there was this one zone where the moisture was dense enough that it was both evaporating and condensing right there in front of your eyes. Yeah, that's right. Yeah, and so yeah, it's interesting. You can go towards the. I've driven by the river sometimes, and they'll like run the barges into the side of the river because they're so worried about running into another barge that they'll sometimes intentionally just bump up against the side on a foggy day because the visibility is so bad. The fog burns off later in the day. It's always in the morning, right, that it's foggy on the river. You know, by noon, it's not foggy anymore because when there's enough sun to burn away, to start heating things up, then the air temperature is increasing, and so that moisture, which previously had to condense because it was supersaturated, the moisture being supersaturated meant that it had to form droplets, and so the fog is droplets of water in the air that are suspended because they're very small. But then as the air heats up again, those droplets just evaporate back into invisible water vapor. So it is the same kind of idea. All right, we've already seen this, a similar figure, not the same one. All right, so the technique we're going to use today for estimating the rate of evaporation has two parts. There are two driving factors and two limiting factors, depending on the way you look at it, in how quickly water evaporates. And energy is one of those two factors. And the energy balance method asks the question, how much energy is available to drive evaporation? The latent heat of vaporization was that 2.5 million joules per kilogram required to go from a liquid to a gas. I'm not sure why that and is there. That's weird. I think that, it doesn't look like that in your notes, does it? And? Well, just pretend it's not there on the screen. All right. So what this does is it says, consider the Reynolds transport theorem, which is basically the idea of we're going to put an imaginary line around some sort of an object, and we want to keep track of what's going in and going out of that imaginary line. And then what happens on the inside of that volume is affected by the transport in and out. So consider, what if we had a tank of water? And that's what this figure is showing. If you had radiation coming in, R sub n, now we already have talked about radiation. We know that anytime there's radiation coming in, there's also going to be emission of heat. And that's what this H sub s is that's the sensible heat that's given up to the atmosphere because that radiation coming in isn't constantly increasing the water temperature more and more and more. But rather the energy that's coming in is doing two things. It's doing the work of evaporation, and it's being radiated back into space. Now, the Reynolds transport theorem, it's saying that the change of mass inside of this control volume is related to the flow in and out of the control surfaces, and that's what this term here is, the sum of the velocity times area. So that's talking about the air. I'm sorry, no, we're not yet talking about air. This is the liquid phase. And so the density sub W here, that's talking about water. And we're assuming that the pan isn't leaking any water down below. But what happens is that the depth of the water is getting lower and lower over time. And so H here is just how much water depth there is. And we're going to define the evaporation rate, E, as the change of height over time. And so here the change of storage, the dV, or V with the cross through it, that means volume. This is the mass that's being lost in this storage inside of the control volume. And so we have a loss of mass over time that's equal to the density of water times the area of the surface times dH dt. And so dH dt has units of meters per second. Area has units of meters, and so that would give us cubic meters per second. And then we could multiply that by the density, which is kilograms per cubic meter, and it tells us the rate in terms of kilograms per second that's going to be lost through evaporation. So this is looking at the mass balance of the liquid and just saying, you know, there is some loss of water that's related to how quickly the water level is going down. Again, that formula is messed up. I don't know. Maybe it just doesn't have the fonts for it or something. If we say that we're going to define dH dt as E, the rate of evaporation, even though the water level is going down, we build that negative sign into our assumption of what evaporation is. Then we're going to define the change in mass over time as the density of the water times the area of the pan and the evaporation rate. So if you have a lake, for example, you could find out how many cubic meters of water per day you're losing from that lake if you know the area of the lake and the evaporation rate. And of course, you'd assume the density of water is 1,000 kilograms per cubic meter. All right, on the other side of things, at first we were looking at the liquid phase. Now we're going to talk about the vapor phase. So the water level's going down, and that vapor, the water that turned into a gas, has to go somewhere. And we can do a mass balance on the transport out of the control surface. And so if we assume that there's no accumulation of water inside of the head space above the pan, this tank, that there's always a constant amount of vapor in the head space, it's going to be going out through the control surfaces. And so this was our rate of evaporation on the left side from the previous screen. Now on the right side, this is interpreted as saying it's the flow through the control surfaces of the water vapor. So Q sub V is just the fraction of water in the mass of water to the mass of air. So the specific humidity is just saying how much of the air is actually water. It's a fraction. And then we have the density of the air, velocity of air, and the cross-sectional area above the pan. So you can rearrange all of that and solve for the rate of evaporation. And it's related to the humidity, the movement of air over the surface of the water, and this is the energy balance method. And it allows us, oh man, all these formulas are screwed up. I guess I'll have to make PDFs next time because the PDFs wouldn't be messed up like this. But at least you have the equations right in your notes. It's not liking that dot, huh? Okay. All right. So let's look at the energy balance method. It estimates E sub r, which is the evaporation rate, by the radiation that's available, where R sub n here is the net radiation. Because it's not just the incoming solar radiation that's driving evaporation, because some of the radiation is reflected off and some of the radiation is emitted as that long wave sensible heat back to the atmosphere. It's the difference between the incoming and the outgoing that drives the evaporation. So R sub n is that difference. Here's the formula on how you can calculate the R sub n if you know alpha, which is the fraction of the radiation that is scattered due to reflectance. L sub V in this formula is the latent heat of vaporization, which is a constant that's slightly dependent on the temperature of the air. And then, of course, we have the density of the water. So in problems like this, you're given some information that tells you how much radiation is coming in, and you're assuming that the only thing that's limiting evaporation is how much energy is available to drive evaporation. You're assuming that there's no limit in terms of how much can be carried away from the surface of the water. Now that turns out to not be true. You know, in this earlier model that we were looking at, we know that anything that evaporates here on this slide, we were talking about, you know, the water level going down. Well, for that water level to go down, the water has to go somewhere when it goes from a liquid into a gas. And we just assume that there's like enough wind to carry it away. Because if all of that humidity just stayed directly above the water surface, then you couldn't have any more evaporation because the air would be full. It would be saturated with moisture. And so, I mean, it's really a two-pronged process that limits evaporation. It's partly about giving enough energy to the water so that it can evaporate, but also it's about transporting that water away from the surface of the water because more can only evaporate when there's room in the air above it. So as a simplification, this energy balance method focuses on the heat input, and let's consider an example where we have a big lagoon. And we can measure the radiation there, the incident radiation, R sub I, 978 watts per meter squared. We know the temperature of the water, we know the air temperature, the relative humidity, and the wind speed. Now, some of this you're not necessarily going to use quite yet. It's going to be these same conditions for a later example, and so the fact that there isn't any place in here that you'd put in the wind speed, don't let that throw you off yet. But what I'd like you to do, though, is try and substitute in the given data here to try and find out what is the E sub R. That's what we're after, is we're trying to estimate the evaporation rate that would occur in a situation like this. And we've got some constants here, like the Stefan-Boltzmann constant. And so I'll just give you a few minutes to plug in those calculations so that you can try and estimate, and the units that you'll get out of E sub R, that's going to be in terms of millimeters per day when you put everything else into the units that are provided. All right, so the first thing that we can do, this R sub E is just estimating how much radiation the water is emitting at a certain temperature. And it's something that could be measured directly with a sensor, but there's a pretty good relationship between the temperature of the water and how much radiation it's emitting. And so you already can get a sense that a good fraction of the incoming solar radiation isn't going to be available to actually drive evaporation because so much of it's being emitted, 452 watts per square meter. And that's out of 978 watts per square meter of radiation coming in. All right. The next thing that we do here is calculate the net radiation that's available. So that fraction of the 978 that's actually doing the work. And so of the 978 that's coming in, 35% of it is being reflected because water has the ability to reflect. Not as much as the snow would be reflecting it, but still it's reflecting some. And so what's left over is 184 approximately watts per square meter. All right. Now for the latent heat of vaporization, I just noticed a mistake in my calculations in the notes. I actually based it on the air temperature. And I noticed that right after I told you it needs to be based on the water temperature because, what we're trying to vaporize is the liquid. And so how much energy is required to vaporize that liquid depends on the temperature of the liquid. And so, I don't think it would have a huge effect on, I think the difference is going to be marginal since the air temperature here in the water temperature are so close together. But this is telling us how many joules are required per kilogram. And we can just substitute that now into the formula for E sub r. And you'll notice I put the units here in each of the steps. Joules per kilogram is the same as a watt-second per kilogram. And so if we want the millimeters per day, that we kind of, it's easiest to think about this evaporation rate in a daily sense because the numbers are so small. When it's just based on meters per second, you can see here 7.6 times 10 to the minus 8 meters per second. But in this case, the 6.55 millimeters per day compares pretty favorably to that average that we saw earlier in the lecture. You know, you always should do kind of like a, they call it sometimes a sanity check or a reasonableness check. And it was saying that the average over the Earth's surface, what was that? Aerial average of evaporation. I don't remember exactly which slide that was on. Was it around like 4 millimeters per day on a 3 on a worldwide basis? And so, yeah, spatial average, thank you, 3 millimeters per day. And so if it is 6 here, it makes sense because this is pretty close to the equator where there's going to be a lot of solar radiation. It's a sunny day with lots of radiation. It's going to drive high evaporation. So this is one part of the equation. It's a two-part thing. As I was mentioning before, part of what limits evaporation is how much energy is available, and then the other limiting factor can be transport. And so we have to think about getting all that newly liberated moisture away from the water surface so that more moisture can evaporate. I think here is a good chance for us to take a brief pause. It's 5 o'clock. Let's take a 5-minute break, and then when we get back together, we're going to talk about that second effect, the aerodynamic method, which looks at transport of liquid. All right, so the evaporation is partly governed by how much energy gets into the water, and it's partly governed by how much wind is going over the water. And this diagram is doing, again, a mass balance, and it's showing that you have airflow above the surface of the water. And you can just sort of, in your mind, imagine that as the water is evaporating, if you're very close to the water surface, then there's going to be a lot of humidity there. But if you get further and further away, then the relative humidity is lower because the airflow is bringing in dry air. And so the faster the air, then that's going to have a kind of like a profile, a humidity profile that's going to reduce the thickness of the boundary layer of where the relative humidity is high. And if you have an increase in wind, then that's also going to have an effect because the wind speed isn't the same at every elevation. If you remember back to fluid mechanics, there's something called the no-slip condition, and that is that fluids can't slip over each other frictionlessly, that there is always going to be resistance to fluid flow. And so a stationary surface like that water is going to resist the movement of the fluid over it. And so if the air is flowing to the right, then there's more resistance at the surface, but as you get further and further away, then that resistance decreases. And so the air at a high elevation is moving very quickly, but right at the water surface, the air isn't moving at all. It has the same velocity as the water that it's touching. And so what this diagram is showing is that as you get higher and higher away from the ground level, or in this case the water level, then the wind velocity is increasing. And so the faster the velocity of the wind, then that's going to change the profile of that, the slope. And so a higher velocity is going to improve the evaporation rate for a couple of reasons. Another one of them things that we have to remember is the adiabatic lapse rate. And this is just simply showing that as your elevation increases, the air temperature is decreasing because of that effect of expanding gases have a reduction in temperature. And as a result of these two things, the specific humidity is lower at high elevations. And the specific humidity we can think of as how much water is in the air relative to how much potentially could be there. And so right at the water surface, the humidity is very high. Sounds delicious. No, do it all at once. Let's get it over with. It's like an old lady with a candy wrapper at the opera, you know? You just want, come on, speed it up. All right. So the point is that what we ideally want, if assuming we care about evaporation, let's say if we want evaporation to be quick, then we want to have dry air touching that water surface. And so I told you at the beginning of class, I've been thinking about evaporation because I've got all this maple syrup I'm trying to make. And so maple syrup is two things. It's sugar and water. And I'm trying to get those two things separated because what comes out of the tree has very, very little sugar in it. I have to boil away 49 gallons of water to get 1 gallon of syrup. And it's like basically a 50-to-1 ratio. And so I've got a lot of water that I have to separate. And so in my case, I'm trying to encourage as much evaporation as possible. And the way that I can do it is by providing heat. But then the other part of it is if I direct a fan at the surface of where that liquid is, then I'm bringing dry air and I can increase the rate of evaporation because right above the water surface or right above the syrup surface, you can't have very much evaporation if all of the spaces to hold water vapor are full. You know, like if it's fully humid and fully saturated with water immediately above the water surface, then that limits evaporation. So the aerodynamic method basically is a way of calculating how effective is transport at moving away the water vapor that's escaping from the liquid phase. And it's a pretty strange empirical method that the E sub A is saying the evaporation rate based on the aerodynamic method. And it takes into account the wind velocity and the surface roughness. And so how wavy is the water is taken into account here. This Z naught, the water surface roughness, kind of depends on, if it's windy, you're going to have choppy water, and then that choppy water increases the surface area, and so there's more evaporation for that reason. You have to take into account the air temperature to try and estimate the saturation vapor pressure, and the saturation vapor pressure and the ambient vapor pressure, so the EAS and the EA, those are both about looking at how much water is already in the air. And so the difference between the two is going to increase your evaporation rate. And so if you want a lot of evaporation, then what you're hoping for is a big difference between E sub AS and E sub A. So a big difference between the ambient air, the ambient vapor pressure and the saturation vapor pressure, because it's a driving force. And so you remember when she had boiling water and she threw that boiling water into the air and it turned into a vapor very quickly? It's because there was a big difference between the temperature of the air and the temperature of the water. And that led to a big difference in the saturation vapor pressure and the ambient vapor pressure. So the ambient vapor pressure was very, very low because of the cold temperatures. And the saturation vapor pressure of the water that she had in the tea kettle was very high because it had just been boiled. And so the big difference between those two things is in part what helped to promote the evaporation being so quick. Okay, so we're going to do the same data, now just looking at the aerodynamic side of things. And so you'll notice now in this series of equations, and I've provided it in the order that you should do the calculations. So the first thing that you'll need to estimate is the E sub AS and so on. So in this case, the aerodynamic, and by the way, the temperatures that you'll put in here, these T's will be Celsius. They won't be converted to Kelvin. It's not using the radiation in this series of calculations. It's just looking at things like the height of the water ripples. So the Z naught here is, how wavy is the water, the wind speed, and the elevation that the wind speed is measured at. The calculations that we'll do here, hold on a second. All right, yeah, so yeah, it is just this order. So first find the E sub AS, then with the relative humidity you can find the E sub A, and so on. I just wanted to point one thing out, and that is when you're calculating the B, since you're doing a logarithm of ratios, the units of Z2 and Z naught have to be the same. And so you're given the Z naught in centimeters, and then the Z2 is this elevation that the wind speed was measured at, 2 meters. So you'll need to either put the Z naught into meters or put the Z2 into centimeters to make sure that there is units consistency in that ratio. All right, well, let's just take a look at where I was going with things. Okay, so the E sub AS that you get should be around 3893 pascals. Is that right? Yeah. Okay. And then we simply multiply that by the relative humidity to get the E sub A, which is 2141 pascals. And then if you substitute that into B, I think we should be getting 0.0036 millimeters per day Pascal. And then finally, we can put it into the E sub A formula and get, I got 6.3, it sounds like 6.1, 6.2, depending, I think, just on round off, probably. All right. So Tyler's question was about, is this happening at the same time? And the answer is yes, that this is simultaneously a windy day and a sunny day. And so both of the things that we need for evaporation are happening simultaneously. But you can't have two different amounts of evaporation because aerodynamics says it's going to be 6.31 and energy says it's going to be 6.55. I should change this example to make that difference bigger. I should maybe change the example so there's less wind. If I gave it less wind, then aerodynamic would be saying that there's less evaporation. The way that we reconcile those two different methods is the combined method. The combined method will include both an analysis of the available energy and an analysis of the available transport. Transport was the aerodynamic method, and it looked at the wind moving away the humidity. And the energy method was looking at the latent heat of vaporization, providing that latent heat of vaporization. Now, here is the combined method, and it's kind of like a weighted average. And the weighted average depends on something called the psychrometric constant. And at one time I knew what the psychrometric constant was. Now I just assume the constant is fine. I had to do a research project a couple of years ago where I was doing a water balance for the Greenbrier, not the hotel, like the watershed. And I had to calculate a specific psychrometric constant for that area, but it was pretty close to this constant. Now the gradient of the saturated vapor pressure curve, though, is something that will vary based on the conditions of the temperature of the air and the E sub AS. And so this weighted average is one way of finding out, which of the two really governs, or which of the two, the energy or the aerodynamic method, which of the two is limiting. But what most people do, instead of actually a full-blown analysis of the combined method, most people would just calculate the amount of evaporation due to the energy balance method. So E sub R was that first thing that we did, and then they say it's 1.3 times this empirical factor, delta divided by delta plus gamma times E sub R. So let's do both of those. Use the combined method and see what we get out of that, and then compare it to the Priestley-Taylor, which is just kind of a simplified way that only relies on the energy that's available to cause the latent heat of vaporization. So, yeah, let's do this as an example. What you'll do is, first of all, calculate delta, and you'll use that along with the given gamma to calculate the actual E in the combined method, and then compare that to the Priestley-Taylor simplification. Can't wait. All right, so, boy, sorry guys, I'm going to redo these notes next time. This is sure sloppy. You can see just how bad my handwriting actually is right here. All right, so did you get delta is 225.8? Okay, so like I said before, this is kind of like a way of figuring out, it's got to be somewhere in the middle. Our two extremes was 6.6 if there's limitations on energy but no limitations on transport, 6.31 if there's unlimited energy but transport is limited, and so the weighted average says it's going to be somewhere in between 6.54 millimeters per day. And if you do the Priestley-Taylor approximation, then that should be in the neighborhood of 6.62, I think. So, okay, so that's a glimpse at how you can use environmental data to predict what evaporation will be. But what we've been talking about here is we've been talking about evaporation of free surfaces of water. Water doesn't leave the Earth's surface only from free surfaces. It also leaves from evaporation from soil. There's also evapotranspiration from crops. And so that's what we're going to be talking about next, is we're going to be transitioning in two ways, because this was all about evaporation from free surfaces, and it was using, like, what kind of data did we use to do that? It was like measured meteorological data. Or if you wanted to estimate in the future, then you'd predict for a certain wind speed and for a certain global radiation based on past measurements. There's another approach to all of this that has its grounding in agricultural sciences, looking at evaporation of crops and how much moisture has to be added to a field when you have a difference between how much water is coming in from the plant due to rain and how much irrigation you can add either by sprinkles or by flooding a field. These pans are a way that over many years crop scientists and agronomists have found to estimate what the demands for water are of a variety of different crops. And so what you would measure with this, evapotranspiration, ET, that word, oh, it's not here on the screen yet. It's just saying evaporation for now, but ET actually stands for evapotranspiration. I guess that's implied because you're saying crop. Transpiration is when plants are losing moisture. Evaporation specifically is just when there's a loss of water from a free surface into the air. Now, these pans have been calibrated to relate how much observed evaporation there is from a pan of water compared to how much evaporation you see from an actual crop. And so there are tables like these where, for example, here in case A, what you would do is you'd measure how many millimeters of evaporation there was in a day from a pan, and then you'd multiply it by a coefficient, K sub P, and that's what all these values are. And you'll notice all of these coefficients are less than 1 because plants hold on to water more efficiently than just a free surface of water because some of the surface of a plant is cellulose, and water isn't going to evaporate through cellulose as quickly as it will when it's just a free surface of water. So that's the first thing I wanted to point out, is that all of these factors are less than 1. Now you'll see it's taking into account the wind conditions, and there are different pan coefficients depending on if it's light wind, moderate, strong, very strong. And then the trend here is that in light winds, for example, let's take for a mean humidity of medium. This top one is saying 65, 60, 50, 45. So it's saying that if you have very strong wind, then what you can expect is the evaporation of the crop is actually going to be lower than if you have light winds. And that's a pretty unusual trend that we're observing there, that the evaporation is going to be lower, but it actually has to relate to the relationship between the pan and the plants. And so the pan itself would have a lot more evaporation in heavy winds. It's just that the plants aren't going to lose as much water as the pan itself would. And so don't be confused by changes in Kp and what you know about how the evaporation in the pan would be happening. And so, just to put that another way, we know from our previous discussions that heavy winds is going to have a lot of evaporation compared to light winds. But what these pan coefficients characterize is how much the plants and the pan deviate, because you've just got some free surface of water and it's surrounded on all sides by grass or by a crop. And you're trying, in this E sub T naught, you're trying to predict what's going to happen for the crop. You're not trying to predict what's happening from the pan. You're trying to say, I'm setting out this pan as an indicator of how much moisture my corn lost today, for example, so that you may have an idea of how much irrigation has to occur in the next day. And so winds is a factor, and also each of these rows is related to an upwind fetch of green crop. And what that's talking about is if your pan is surrounded by a green crop, then that may, the green crop is going to hold on to humidity in a way that is going to affect the pan. And so if you only have 1 meter upwind of your pan that's a green crop, there's going to be a different Kp than if you've got 1,000 meters upwind. And so there's a closer relationship between the pan and what the crop is doing if you've got a long distance upwind of the crop. Now, this case B is just when you have fallow earth, and so bare area that isn't planted with a certain crop. And so just to get an idea of how these calculations work, what we can do is we can substitute in, well, it's not really a substitution, it's just looking up off of the table. If we have an area where it's 2.7 meters per second is the wind speed and a relative humidity of 65%, and we've got this pan set out in a corn crop, oh no, it's fallow, okay. 100 meters of fallow on all sides, and it's measuring 4.2 millimeters of evaporation per day. All right, so that 4.2 millimeters of evaporation per day is E sub P. That's the evaporation of the pan. So E sub P is 4.2 millimeters in a day. And we can go back to this table, and it's surrounded by bare area, and the wind speed would go into the moderate, because the 2.7 would put it in a moderate wind speed. And now we do the upwind fetch of dry fallow is 100, and then our relative humidity in that example, it was saying the relative humidity was what, 45%? Oh, 65, okay. But that still is in the medium relative humidity range. And so the K sub P that we should use here, K sub P should be 0.60. And so, and this is an awfully simplistic way of looking at it, but you can estimate that your evapotranspiration is going to be 0.60 times the 4.2 millimeters per day. Okay, so if we multiply that 0.60 by 4.2 millimeters per day, that is 2.52 millimeters per day. And on a monthly basis, that means that would be 75.6 millimeters per month is how much evapotranspiration we could expect for that bare fallow. So evaporation from a bare fallow. A fallow is just a field that's not planted, and so it's got weeds. It may have, like the earth maybe has been tilled, and so it's still just like some bare soil areas as well. Now, the example asks the follow-up question of what if we had the monthly reference evaporation for short irrigated grass turf? Oh, it's the fallow on all sides. All right. So the pan was surrounded by fallow, but this is actually how much evaporation we would see from the grass turf. And I guess I should clarify that this table is for grass turf, but the case A and the case B is about where the pan is located. If the pan is surrounded by a short green crop or surrounded by the bare area. Now, how much irrigation should the farmer provide isn't necessarily the same amount as the evapotranspiration, because you still have precipitation. And so just as a concept, irrigation is going to be the difference between evapotranspiration and the precipitation, because how much natural rain occurs is going to reduce the amount of external water that has to be provided. And so the irrigation plus the precipitation amount will equal the evapotranspiration if you assume that there's no accumulation. And this last part of it, will the evapotranspiration be more or less for corn compared to grass? So what would your expectation be? If we weren't worried about like turf, if we were actually worried about a crop of corn, do you think that the evaporation is going to be greater or less for corn? Why do you think it would be? Why do you think corn would evaporate less water than grass would? Okay. So you...
Yeah, corn is higher.
Okay. It's thicker. Well, I can see your points there. At the same time, now think about the surface area of the plant, because the water is migrating out into the air through the outside, like through the leaves. And, a corn stalk is much taller, and it has much greater surface area compared to grass, which is maybe an inch tall, 2 inches tall. And so the other factor, in addition to having greater surface area, the corn is higher up in the air where there's more wind potentially. And it varies from crop to crop. I found some data online that addressed that. And using grass as a reference, then it's talking about some crops need more water and some need less, but of course it also depends on what the conditions were like, and so there's a range here. And so in the case of maize, or corn, it's saying that in general, corn is going to require about 20% more than grass would. And there can be a range here. If you have humid and calm conditions, maybe it would be close to the same amount as grass would, or if it's very dry and windy, it would require maybe a lot more. But there are some crops like onions and cabbage, or in some cases cotton, that requires less than the grass would. And then one other kind of interesting figure that was online was showing the same kind of thing, using grass as the reference, and for different crops. Here's corn again. Maize is higher than the grass. But in the case of pineapple, what's interesting about that is that it requires so much less water because when the sun comes out, part of the pineapple tree, or not tree, but it's like a bush, it closes during the day and opens at night. And so it loses a lot less water because the stomata, I think it's called, is opening and closing through the daily cycle, whereas most crops don't do that. Most of the crops will open up and try and expose more of the leaves towards the sunlight, and then that increases the amount of evaporation during the day. The pineapple is kind of unique because it doesn't do that. But the idea is just that you can use the pan to predict how grass would evaporate, and then you can use the reference between grass and other crops to know how much irrigation maybe has to be added to a field. And so it's a very quick and dirty way of estimating the evapotranspiration, this using of a pan. But it does account for both of the factors, because if you have a pan of water sitting out in the field, then it's going to be affected both by whether it's a cloudy day versus a sunny day. It's going to be a direct reflection of whether it was windy versus dry. And so it's exposed to all of the same conditions as the crop. And so it can be useful in that way. All right, so everyone has a copy of the new homework assignment, right? All right, I just want to show you what data you should download. So I'm going to go to MU Online, where I have a copy of the assignment posted. What you're going to be doing is just the same combined method. Do I give you wind data, or just to the link to, okay, energy balance method? I think that you're not doing the combined method for this one. I think you're just doing the energy balance, which was the first one that we did, because you can get solar radiation data for stations all across the U.S. And, okay, here's the homework assignments. Pan evaporation is easy enough to get. Here's the pan evaporation averages. But what's a little bit more tricky, the first time I clicked this link it wasn't working, but let's see if it is now. Okay. Okay. I want the link. So strange. All right, so okay, here's what you're going to have to do. We browse to the new site. I did this earlier, and then when I clicked on it the next time, everything I needed was there. Oh, that's not it. That's not it either.
I think you just covered the whole link.
Yeah.
1991.
Okay. What's the rest of it?
That's 2005 slash element slash site slash.
Okay. Yeah, glad you noticed that. Okay, so 1991 slash, okay, through 2005, hourly site on fly.cvi. ID equals 7236. What's the other one? 50? Oh, so, no, that's right. I know it's there. I got it just today. Okay, yep, this is where we're going here. Mexico. And look, this is going to be, when I click on this, it's going to be the same link that I just put in. New Mexico, Albuquerque Airport. That's the same one, right? Oh, is that it? Oh, they've updated. Okay. So that's the issue. All right, so change that link. Not 2005, it's 2091 through 2010. All right. Okay. So they added more data, even better. So what you're going to do is get the data for 2005, and it's a CSV file that this will be easier to read than that weather data file was because the columns aren't going to be messed up for it. But I'll point out the column that you need to use for it. Okay. It's this one, right? Sunny glow. That's what it says on the paper. So what you'll need to do is scroll down to the day in question, because these have measured different days, and it's not the same amount of solar radiation every day, because the solar radiation is changing, and this is hourly, hour by hour, so 8 o'clock, 9 o'clock, 10, 11, 12, and so on. Some days are cloudy. In the summer, the sun is more intense than it is during the winter time, so what you'll need to do is go down to the day that it's indicated, and then use this as the radiation input for applying the energy balance method. All right. I'm glad we got to the bottom of that mystery. That's another thing I'll have to change, though, is the link that I pasted in there. All right, that's all we have for today.